In this class, we are going to see what is a two-dimensional DFT. So we simply discuss what is a two-dimensional DFT. How will you find out the two-dimensional DFT of an image and its inverse? Okay, so we have the equation for a two-dimensional DFT. Two-dimensional DFT is given by FKL, that is sigma m sigma n fmn. Fmn is my input image. I consider fmn is of size n by n. So my m ranges from 0 to n minus 1 as well as my n ranges from 0 to n minus 1. Then you will be having wn raised to kn and wn raised to ln. Okay. So here we can simply consider this expression as fkl equal to your input image multiplied by some basis function. This basis is a separable. When I consider the separable transform, this basis I can write one is wn raised to km, then another one is wn raised to ln, where you can see fkl. I have two dimension, one is k and l. Similarly, when in the spatial domain I have m and n. Okay, so one is wn raised to k and m, and second one is wn raised to l and n. Okay, then when I write down the inverse, I have the equation for fmn. Only difference is here I will be having my wn raised to minus km and wn raised to minus ln. So one basic property of this DFT is this is basis function is always a exponential term. Okay. So we can move to the next slide. So when you consider the case of a two-dimensional unitary transform, only difference in the expression is I have a term 1 by n outside for both the expression, both the equations. So here I have a term 1 by n outside, here I have a 1 by n outside. All other equations are the same. So as we said, this wn is my basis function. For a DFT, this basis function is an exponential term. So I can rewrite this expression by substitute for wn as an exponential term. So I can write down the expression for fkl equal to, all these terms are the same. Then substitute for wn is an exponential term, that is e raised to minus d 2 pi by n. So wn is e raised to minus a 2 pi by n. Then I have raised to km raised to ln. So wn is the same. So you have a raised to m into a raised to n form, so that you can simplify it as a raised to m plus n. So I can write wn as e raised to minus a 2 pi by n raised to km plus ln. So e raised to minus a 2 pi by n into km plus ln. Here also in the equation for fmn I can substitute for wn. So in the equation for fmn, I substitute for wn is equal to e raised to j e raised to minus j 2 pi by n. So here I have a negative sign. Okay, so minus of minus it will be plus. So e raised to plus j 2 pi by n into km plus ln. So this is an expression for two-dimensional unitary DFT. Okay, so here for unitary DFT I have a term 1 by n outside. For both the equations I have a term 1 by n outside, and the basis function is always an exponential term, that is e raised to minus j 2 pi by n. Now we can see an example. So here we have seen fmn is my input image. Fmn I can represent it by coefficient multiplied by some basis image. Okay. So when you go to the previous slide, you have this is expression for an image fmn equal to fkl multiplied by all others. We can consider this 1 by n into e raised to j 2 pi by n into km plus ln. This we can consider as a basis. Okay, so your input image can be represented as the inner product of the coefficient with the basis. So 1 by n into e raised to j 2 pi by n into km plus ln is your basis. Okay, so this I can represent it as fmn as inner product of fkl, that is fkl is your coefficient with basis. That basis 1 by n into e raised to j 2 pi by n into km plus ln, I represent it as hklmn, that is a function of k, l, m and n. So I represent it as HKLMN. Okay, this HKLMN, I can apply the separable property and I can represent it as HKM into HLN transpose. Okay, I can apply the separable property that this two-dimensional basis, I can represent it as a product of two one-dimensional bases. So one represented as a column vector and other is the transpose of L. That means it is a row vector. Okay, this two-dimensional basis can represent it as a product of two one-dimensional bases. So I can write down the expression for HKM. HKM equal to, so in your expression, 1 by n into e raised to j 2 pi by n into km plus ln is your basis. So here by separable property, I can separate HKM and HLN. So HKM means I take the first term, this e raised to j 2 pi by n into km. Then I have a term 1 by n outside, so I take 1 by root n with one pair and 1 by root n with another pair. Okay, so 1 by root n into e raised to j 2 pi by n into km is my HKM. Then 1 by root n into e raised to j 2 pi by n into ln will be my HLN. Okay, so HKLN, I separate it as two one-dimensional bases, HKM into HLN transpose. So HKM is 1 by root n into e raised to j 2 pi km by n. Similarly, HLN will be 1 by root n into e raised to j 2 pi ln by n. Okay, so that your total coefficient multiplied by HKM and HLN transpose would be here HKLMN. Clear? Now I start with HKM. As we know, M ranges from 0 to n minus 1 as well as K ranges from 0 to n minus 1. So I write down the expression for HK. So M ranges from 0 to n minus 1. I have 1 by root n. 1 by root n I can take it outside. You know this is a one dimensional. So I have 1 by root n, take it outside, and this will be a column vector. So I substitute for M equal to 0. M ranges from 0 to n minus 1. M equal to 0 means you will be having the first term e raised to 0. E raised to 0 will be 1. Then M equal to 1 means e raised to j 2 pi k by n. Then M equal to 2, M equal to 3, etc. up to M equal to n minus 1. So this will be my HK. Okay, HK obtained by substituting M equal to 0 to n minus 1. So that will be a column vector. Similarly, when you write down the equation for HLN, it will be again a column vector like this. Then you have to take it transpose, then multiply HKM with HLN transpose, so that you will be getting a two-dimensional vector HKLMN. So I just consider a case where n equal to 4. When n equal to 4, my M will ranges from 0 to 3. Okay, so I can write down the expression for HK. HK equal to 1 by root n. Okay, here n equal to 4. So 1 by root 4 means 1 by 2 into e raised to M equal to 0 means I will be having e raised to j 2 pi k by n equal to 4. 0. Then e raised to j 2 pi k by 4 into m equal to 1, m equal to 2, etc. up to n minus 1, that is up to 3. Then I have to solve for this. So here k also varies from 0 to 3, 0 to n minus 1. So I can solve for h equal to 0. H equal to 0 means I have to, h0 means substituting k equal to 0. So substituting k equal to 0 means I will be e raised to 0. Second time is again e raised to 0. Third term k equal to 0 means e raised to 0. Fourth term e raised to 0. So all the terms will be equal to. Similarly, we can find for h1, h2 and h3. So for h1, I have to substitute k equal to 1. So k equal to 1 means here I have m equal to 0. So e raised to 0. First term will be e raised to 0. Just note, for k equal to 1, I have first term e raised to 0. For k equal to 2, again e raised to 0. K equal to 3, e raised to 0. For all the cases hk, for all hk, my first term will be always equal to e raised to 0. That is, my first term will be always equal to 1. Then I have to find out for the remaining term by substituting k. So for h1, I have e raised to j 2 pi 1 into 1, 1 by 4, e raised to j 2 pi by 4. So e raised to j theta. I have to find e raised to j theta. You can use a calculator to find e raised to j theta. e raised to j theta is actually given by cos theta plus j sin theta. E raised to j theta is cos theta plus j sin theta. If it was e raised to minus j theta, it will be cos theta minus j sin theta. So you can just use a calculator to solve for e raised to j theta. E raised to j theta equal to cos theta plus j sin theta. So solve for it. So e raised to j 2 pi by 4, cos 2 pi by 4 will be 0. Then sin 2 pi by 4 will be 1. So I will be having 0 plus j1. So my answer will be j. Similarly, solve for all this using your calculator, cos theta plus d sin theta. Similarly, you can solve for h2 and h3. Since I have n equal to 4, it varies up to k varies from 0 to 3. So we will get up to h3. Now, I have find out the one-dimensional HK. Now I have to find out the two-dimensional basis HKL. So HKL equal to HK into HL transpose. So if I want to find H00, H00 will be, I have to take H0 into H0 transpose. Okay. So you already calculated the value for H0. So H0 was 1 by 2, 1, 1, 1, 1. So to find H00, H0 into H0 transpose. So you have to find H00. So for finding H00, I have H0 is 1, 1, 1, 1 into H0 transpose means I will be having a column vector multiplied by a row vector. So do the multiplication. You will be getting H00. So I have 1 by 2 outside for both cases. So I will be having 1 by 4. So 1 by 4 is outside. Then I have to multiply HK and HL transpose. So HK, as we know, it is 1, 1, 1, 1, 1, 1, 1. That is my HK into HL transpose is HL transpose is a row vector and HK is a column vector. So it will be having 1, 1, 1, 1. So I have to multiply these to get my H00. I have 1 by 2 common for both the cases. So I have a 1 by 4 outside. So I will be having 1 by 4 outside. Then I have to multiply this to get the two dimension. So I will be having first row into first column. So that will be 1, then first row into second column. Again will be 1, then this into this 1, then 1 into 1, 1. Now I'll go for the second row. Second row into this column 1, then second row into second column 1, then second row into third column 1. Like that I can do all the multiplication. So I will be getting the matrix like this. So this will be my H00. Similarly, I have to find H01. So for finding H01, I have to take H0 into H1 transpose. So here I will be having H0. Then H1 transpose. I have to replace this with H1. Again I have 1 by 4 outside. Multiply, you will be getting H01, H02 up to 3, 3. Okay, H33. So we can find up to H33. Now, if I have the value for f is my coefficient. If the value of f is given, I can compute the value of my image. So this small f is my image. Okay. So in order to get the image, you know it is the inner product of coefficient with the basis HKL. So in order to find f00, what I have to do is I have to take the inner product of f with h00. So I have 1 by 4 outside h00. This is my h00. Then into f. So what I do is I have to take the inner product. So I have to multiply each element by element. 1 into 1. That is 1 plus 1 into 2. That is 2 plus 1 into 2, again 2 plus 1 into 0, It is 0 plus, then again 1 into 0.